Welcome everyone to the June General Meeting of the Kalamazoo Astronomical Society. I want to thank you all for joining us on this wonderfully warm and sunny day. It is tough to be inside, but I promise you it'll be worth it because we do have an excellent guest speaker tonight. And I don't want to waste any time. I want to introduce him right away because I've been waiting a long time for this. So, tonight's guest speaker is a senior astrophysicist in the Observational Cosmology Laboratory located at NASA's Goddard Space Flight Center in Greenbelt, Maryland. He is also the senior project scientist on the James Webb Space Telescope, scheduled to launch on October 31st, 2021. As senior project scientist, he leads the science team and represents scientific interests within the project management. His research centers on infrared astronomy, cosmology, and the development of new instruments for exploring the universe. He was the project scientist and the principal investigator of the legendary Cosmic Background Explorer, COBE, with which the leftover radiation from the Big Bang was measured precisely for the first time. He has received numerous awards, including the Nobel Prize in Physics with George Smoot in 2006. Time magazine named him on its 100 most influential people in the world list in 2007, and as one of 25 most influential people in space in a special issue on new space discoveries in October 2012. So without further ado, please welcome Dr. John C. Mather.
Well, thank you. Thank you for the great introduction. I always have to remind people that when all these great honors come to someone, they are actually always representing a team of some sort. So I'll tell you a little bit more about the work that was done. And now we'll put up my screen and show you the charts, of course. Always come with my view graphs. So here they are. I want to show you the telescope that we're building now, the James Webb Space Telescope. There it is in the middle of the picture, a gigantic golden hexagon. That golden hexagon is 6.5 meters across. Can we use metric units today? Anyway, 6.5 meters. It's about 2.5 times larger diameter than the Hubble Space Telescope, which is 2.4 meters. And it's extremely powerful because it does something different from what Hubble can do. This telescope is designed to observe infrared light that you cannot pick up with the Hubble, which is why it's special and different. I'm showing you on this little introductory chart that this is a joint international project. NASA is the leadership of it, but European and Canadian space agencies are chipping in a lot to make this thing a reality. So we'll come back to it later to show you how it really works, because this is a telescope unlike any other. So if you're an astronomer, you can send us a proposal and say, please look at my favorite target over there. And if you have a good story about it, we will possibly look at it. So it's taken many thousands of engineers and technicians, well over 100 scientists, and we are anticipating that basically all professional astronomers will be using it. So thanks for coming to hear the story. I think it's an amazing story to tell. So I'd like to start, however, back at the beginning. The question that has motivated me since I was a child is, well, how did we get here? And I think everyone knows now that the universe is expanding, and that's what we call the Big Bang at the beginning, although that's a tricky question. We know that it's unstable because it wasn't always full of stars and galaxies. It has been reorganizing itself and releasing energy in the process, so that's what makes it reorganized. It's so enormous and so old that even very rare possibilities, such as you and me, have had a chance to come into reality. We have learned about stored information. So we know that our individual living cells use DNA to record their digital instructions. And we don't usually picture the fact that our body is made out of 30 trillion, roughly, digital computers, all hooked together by electrical and chemical signals. But they are. That's what they do. They read the code of the DNA and they do something. So the secret decoder ring of the DNA decoder is something that we may never fully understand because it's complex. At any rate, this has enabled us to be here. It has enabled evolution. And I point out that this is what I call survival of the lucky. A long time ago, when Charles Darwin gave us the story of evolution, people said, well, obviously people are destined to be at the top of the pyramid, so evolution was directed to produce us. I think these days we have a little more humility about that. We say, thank you, I'm glad to be here. There is good evidence from the genetics that the population of all human beings was down to a few thousand people, maybe 100,000 years ago when there was something like about bad weather somewhere. So a little bit uncertain about all that, but we should not assume that we are the top of the pyramid because we're supposed to be. We've also learned about what I call nested feedback loops. Every one of those 30 trillion digital computers in your body runs according to some mathematical control systems that stabilize it and keep it running. And when it's time to die and replace itself, the body knows how to do that too. So this is what we call in biology homeostasis, keeping everything the same. And that's why even though most of my atoms have been replaced since I was a child many, many times, you still think I'm the same person, which is pretty tricky, eh? So how does that work? Well, we've heard that from physicists that there are 4 kinds of major forces: the strong nuclear force, the weak nuclear force, and the electromagnetic force, plus gravity. So those control how the parts fit together. So you can say, well, we've got a handful of different kinds of particles. Protons, neutrons, electrons are the ones we see now. And then the quantum mechanics tells you the rules of the game, how the Lego blocks fit together, how much energy is released if they stick together in a certain way. And that is the secret of the complexity of life. We are here because of all those quantum mechanical stories that how the particles fit together. I will show you a little bit about how the gravity works, and in particular, point out that although you learned in school that things do not spontaneously heat up, nevertheless, in nature, things do. And that's because gravitational energy can be converted into kinetic energy, which means they get hotter. So in thermodynamics, we know about entropy, and we know that entropy increases and never decreases. And curiously enough, when things are not in equilibrium, nature often finds a way to increase entropy by producing a spontaneous heat engine, which takes energy from one place, transports it to another, and produces a complex system to help it do it. So that's us. We are helping the universe increase entropy by doing what we do. Other people say, well, why are we here? It's because the plants need the carbon dioxide. But I think that's actually too simple. So astronomers figured out over a century ago how about this instability, how it works. So you see this beautiful picture, which is called the Eagle Nebula. This is a place in the sky where gravity is pulling clouds of gas together surrounded by a lower gas pressure. And how is this doing it? Well, when the gravity is enough to overcome the pressure of the gravity, this cloud of material can pull itself together and become a smaller object, eventually turning into stars, for instance. So the size of that is governed by the speed of sound. If it takes less time for a sound wave to cross this object than it takes for the object to fall in, then it controls the rate, whether or not it can collapse. So this is a place where the universe heats itself, converts gravitational energy to kinetic energy. So now we need, of course, to know the details. How does that really work? So here's an example of a spontaneous non-equilibrium process. This gigantic Hurricane Harvey was hovering over Houston, Texas a few years ago while we were testing the Webb telescope in the vacuum tank in Johnson Space Center in Houston. So that's something we're very familiar with. So how does this happen? Well, it's hot at the equator, it's cold at the pole. There's an energy flow from equator to pole. And so this spontaneously occurs. It's like a very complex circulation system will increase the rate of transport of heat from equator to pole. So that's something that we have seen over and over again in nature. And we're examples of spontaneous organization that increase entropy. So living things. So to get to, however, the more astronomical part, which is simpler, let me show you the original chart that gave us the idea that the universe is expanding. So back in 1929, the same year that the worldwide economic system collapsed, Edwin Hubble drew us this chart. It shows distant galaxies on this chart, and each little dot there is a galaxy. So a galaxy, except for 4 of them in the lower left corner, they're all going away from us. So what you see also is this trend plot, but the farther away they are, the faster they're going away from us. So in 1929, this was the first evidence that we had that the universe even had an age, and by dividing the distance by the speed of motion of each galaxy, you can get an estimate of that age. So 1929, we were forced as scientists to take in a huge surprise. And of course, there was a mistake in this plot. The distance scale was incorrect because Edwin Hubble was using Cepheid variables to estimate distances, and he thought that the distant Cepheid variables were the same kind as the local ones, but they weren't. Anyway, 1929, we were forced into the idea that the universe is expanding and different distant things are running away from us like crazy. Also, from our perspective, it's important that they're in the lower left corner are these 4 little dots, because there are some galaxies that are headed in our direction. It's going to be very exciting. So it was predicted from the idea that the universe is expanding that it must have been very hot when it was young. And if that's true, then it should have been hot enough that the heat radiation should still be here. So Ralph Alpher and Robert Herman predicted this back in 1948. Nobody went to look for this heat radiation of the Big Bang, but we did finally get it discovered by accident in 1965, while another lot of people were building their apparatus to hunt for it. At any rate, that was 1965 when it was discovered. In 1970, I was a graduate student in Berkeley, and they said, here's a thesis project idea. Let's go measure that radiation. As it happened, my thesis project failed to function properly, and I got a thesis about a failed project. I went off to NASA in New York City, got a job to become a radio astronomer. But as it happens, NASA also said that summer, well, we're interested in new ideas for satellites. We've just 5 years ago, we landed on the surface of the moon. We're almost done with landing people on the moon. So what are we going to do now? Let's try science, some more science. They thought they'd get a few proposals. They got 150 proposals, including one from my friends. And I was the lead person writing that proposal. So we all thought, well, it's unlikely that this will be selected because the competition will be great. But nevertheless, it was chosen for further study. And 15 years later, in 1989, it went into space, and this is what it looked like. So the purpose of it was to measure the heat of the Big Bang, see if it's the right color, and does it come equally from all directions. So here's the first measurement we got. It took us just a few weeks after launch to get this picture. The curve that you see there on the picture is the theoretical prediction. It's called a black body curve. It shows how bright the radiation is at each different frequency in terms of waves per centimeter on this chart. And you see all the little boxes, they're almost all exactly on the curve. So why would that be? Well, that's because the early universe was a pressure cooker, and the heat radiation was able to come to this ideal black body form almost immediately. And the expansion of the universe didn't wreck it. So there it is. It still follows that exact curve. Eventually, we got the error bars so small you couldn't see them. We got a standing ovation for showing this chart at the Astronomical Society. And I thought, well, doesn't everybody know that was the right answer? But of course, you don't always know. There is no answer book except the universe. So got a standing O for that little chart. So a couple of years later, we were able to show this chart. And these three ovals are maps of the sky showing the brightness of the cosmic heat radiation. Each one is a whole sky, each one of those ovals. And the top two we can ignore because those are local effects. The bottom one in the lower right corner is a map that shows hot and cold spots that are after taking out all the local effects. And there are about a part in 100,000 difference in brightness from the total temperature, which was only 2.7 degrees above absolute zero. So in order to get that map, we had to average together hundreds of millions of measurements. And that was pretty tricky. So, but it worked. We showed that map. Stephen Hawking looked at that map and said that was the most important scientific discovery of the century, if not of all time. And so now we know why he thought it was so important. Number one, most of those spots come from dark matter, something that astronomers can deduce, but nobody can see. Number two, we would not be here without those spots because those are the gravitational forces that pull galaxies together from the primordial material. So if they weren't there, we wouldn't be here. Of course, the third reason to be interested is if we ever can predict what those spots are like, then we maybe will understand quantum gravity, which is one of the hardest problems in physics and may never be solved. But at any rate, when we do solve it, it should explain this map. So, okay, what happens next? Well, let's just summarize the story of the universe here. And this is the standard picture. This is not the way the public generally understands it. And that's why I'm telling it to you. So we know the early universe was very hot and very compressed. It has no center and no edge. And when people call it the Big Bang, it's hard for people not to picture a big firecracker, which does have a center and does have an edge. But the universe has no center and has no edge. That means that it's expanding into itself. It also means there's not even a first moment. So although people talk very cheerfully about the moment of creation, it's not something physicists can see. We do not see the original moment of creation. As you imagine the expanding universe, you can imagine running it backwards in your mind. And as you imagine it backwards in your mind, it gets hotter and hotter and denser and denser. And when you run out of imagination, that's what you call the Big Bang. But there is not such a thing as infinity. It is not a thing. It is not a place. And you cannot get there even in your imagination. Infinity means without limit, not a spot. So anyway, so that's the standard picture. If we find a way to escape from this picture, that is to say, what was there before the Big Bang, that will be pretty exciting, but it'll also be hard to know. So that's what we have now as a basic picture of the expanding universe. So what happens next? Well, we have to take pictures to see what happens next. So the great Hubble Space Telescope took some pictures. It's now 31 years old. Can you imagine that? It was launched just a few months after the COBE satellite that made those pictures I just showed you. And it's still working beautifully. But it's the same size as the Mount Wilson 100-inch telescope that goes back to the 1910 or so. So anyway, there's the great telescope in space. And it was used to discover something very strange. Here we've got a little sketch illustrating the galaxies are pulling together with gravity. So the expanding universe must surely be slowing down because of gravity. Well, let's go look. So they went and looked, and these people said, actually, the opposite is true. The universe is accelerating. It's going faster and faster every year. So who knew? Well, actually, Einstein had a place in his equations for this possibility, but almost everybody that I knew said, well, that would never happen. Who asked for that? Anyway, these people did find it. They got their Nobel Prize in 2011. So if we believe this story I'm telling you, then we should be able to run a computer simulation of the formation of galaxies. So what we've done here, or other people have done, I should say, is they've imagined a box of universe, filled it up with random variations of density and temperature, and set it running in the computer to see how does the gravity stop the expansion, pull the material back together to make galaxies. And it turns out to make a very beautiful pattern. I hope the video is feeding through for you, because what it's showing is that the galaxies not only form, but they align themselves into great cosmic strings of galaxies, and even into big flat sheets of galaxies. Here it is in my screen looking big and flat. And in between, there are huge empty voids, cosmic voids. So when the universe is about 4 billion years old, suddenly a lot of things start to blow up. What is that? When stars are formed, they can burn for a short time and then explode in great supernova explosions, or they can turn into black holes. And when material falls into a black hole, enormous energy can be released in that way too. So for quite a few billion years, there were large numbers of these events, huge cosmic explosions in the cores of galaxies. So that was a bad time to be alive. And so the Earth wasn't even here yet at that time. Around 9 billion years after the start, the explosions were slowing down, and that's just about the time when the solar system was being born on the outer edge of one of these little pink blobs that you're seeing orbiting around in front of of our computer screen here. That's going to become a galaxy. So 2/3 of the age of the universe had already passed by the time that the solar system was being born. And I love this movie because it's beautiful and because it shows you things you could never wait long enough to see. So how do you know if this movie is true? Well, you have to go take pictures of the sky and see if they resemble the predictions of a computer simulation like this. So we're getting there. It's not too bad. We're not done either. So, but here's some, here are the names of the people who made this thing work. Millions of computer hours went into this picture that movie that I showed you. So, don't want to show it twice. Come on, machine. So what you're going to do next, we're going to have to go look and take pictures and see as far back in time as you could possibly see. So we are building this telescope, the James Webb Space Telescope, which is named after the second administrator of NASA. And he was the person who went up to Jack Kennedy and said, you know, I know how to get us to the moon. We can land astronauts on the moon in a decade. So Jack Kennedy went and announced to the world that we were going to do this, and we did it. Took us about 8 or 9 years after he had announced that fact, and there we were. We had to develop everything about the human spaceflight program because we were behind the Soviet Union at that time. So huge, huge accomplishment, and is a great person that we should be recognizing for his accomplishments. At any rate, here is a sketch of the telescope again, the great golden hexagon. What you see there in the blue is called a sun shield because it's an umbrella. The telescope is protected from the heat and light of the sun, the earth, and the moon by a 5-layer plastic umbrella, aluminized or metallized plastic. The telescope is fitted out with 4 different instruments that come from the United States, Europe, and Canada, and it will be operated just as the Hubble Space Telescope is operated from the Space Telescope Science Institute in Baltimore, Maryland. So we are planning to put it in a box and ship it to French Guiana for the launch on the European-supplied Ariane 5 rocket. So we'll be able to get there by the end of October, but there is a little difficulty with the rocket itself. So we're going to make sure that they get that fixed before we actually do launch. Anyway, we plan to operate for at least 5 years, and we're carrying a fuel for 10. What are we going to look at? Well, there's 4 main themes that people use to decide what telescope should we build. So the first one was called First Light and Reionization. So we know from the story of the expanding universe that in the beginning there were no stars, and then at a certain time they turned on. In the beginning there was hot plasma, then it cooled off and became neutral gas. After that, at some point, it got ripped apart again. It turned into a hot gas and the plasma again. Now, plasma is electrically conducting. It means the atoms have been split apart into protons and electrons, or helium nuclei and electrons. So that's a pretty important time history for us to find out. Relates to how it is that we got here from the Big Bang. We want to know, how did the galaxies grow? The movie that I showed you says that they are formed for little bits being pulled together into big clouds. It would be great if you could prove that by looking at galaxies as they used to be when they were young. So we look at things far back in time, far away, and we should be able to check this story. We will be looking into the birth of stars. This beautiful Eagle Nebula in the lower left picture is a place where stars are being born as we speak. And you can't see them. The dust that surrounds them makes it possible for them to grow, but it also keeps us from seeing in. So if we used infrared light, that dust would become transparent and we would be able to tell what's happening inside. Finally, we want to know, what about planets? Now we know that most stars have planets, and that planets about the right size to be like Earth and the right temperature to be like Earth are happening around 20% of stars. So there's an awful lot of potential Earths out there, and we would like to know if they're like Earth, or are they not? So that's what we think we're going to look at. Now here is a sketch of how the telescope itself works. It's not quite a Cassegrain telescope. It's an augmented Cassegrain telescope with a third mirror, which is a concave elliptical mirror. And that is used to improve the image quality. We don't have a Schmidt telescope, or one of the various things that you can now buy for amateur telescopes. That's too big. You can't have another full-size something across the front of the telescope, but you can have a smaller correcting mirror at the back that makes the image quality great. So we make what we call a diffraction limited image at 2 microns wavelength. Lambda over 14 is our spec for that figure. It means you get a pretty darn good image if the wavelength of light that you're observing is 2 microns, which is about 4 times longer than the light that you can see with your eye. So how are we going to do this? Well, number one, I didn't tell you yet, but we have to get this telescope to operate at a very low temperature. If it's not cold, it will be emitting its own infrared light, and you won't be able to see the faint things you're looking for. So not only does this thing have to be big and ultra light, because we've got to lift it up into the space on a rocket that's much less powerful than the space shuttle, but we've got to make it cold. So the way we decided to do this was to make that big golden hexagon out of 18 smaller hexagons, and they're made out of thin beryllium. Beryllium that's cut to the right shape. It's about 2 millimeters thick with little ribs on it, and it has to be polished so it will be the right shape when it is cold. So how are you going to do that? Well, you polish it when it's warm. You cool it down to the right temperature that it'll have when it's being used. You measure all the bumps that it has then, and you say, now I'm going to warm it up, polish off all those bumps, cool it down another time, and it'll be right. And that is what we did. So we made 18 really good hexagonal mirrors that have the right shape when they're cold. So we've got 4 instruments on board. They're a combination of cameras and spectrometers. So a spectrometer spreads the light out of a star out into a rainbow, and you use that to get the chemistry of the object and to the way that it moves and the temperature. So we have multiple purposes on here, and the probably the most revolutionary instrument is the near spec instrument. It's come from Europe, and it has 250,000 little micro shutters that open up to let the light in from selected targets. We can observe 100 galaxies at one time and get their spectra. 3 of the instruments have coronagraphs, which means we can use them to hunt for planets orbiting other stars. So how good is this? Well, it has the sensitivity to see a bumblebee at the distance of the moon. That is to say, 1 square centimeter reflecting sunlight and emitting heat at the distance of the moon would be possible for us to see if it could sit there for several days. We needed time exposure, but yes, we could do that. The hard problem is actually looking at bright objects like Mars, where you have to really basically squint your eyes because the photons are coming in so fast. But we know how to do that. Another thing we're going to do is transit spectroscopy. We'll stare at a star and wait for a planet to go in front of us, and that tells us about the planets. So what is this going to be look? Well, here is a picture taken by the Hubble showing some of the first galaxies. And the Hubble team decided to point the telescope at a blank part of the sky where there are only a few stars and basically nothing to look at that anybody knew about. And what they saw was, after spending 2 weeks, then many, many thousands of galaxies in a few square arc minutes of sky. And there's one star in this picture. It's the one with the red and green spikes sticking out of it in the lower right corner. All the rest of these are galaxies. So when the Hubble astronomers got this picture, they said, that's great, but you know, it's not good enough. It's not able to see the first galaxies because they're too faint and too red, and we can't pick them up with a Hubble telescope. Please build us another telescope. And that is what became the James Webb Telescope. We will be looking into those Eagle Nebula kinds of clouds. Here is an example where we show the difference between the infrared view with Hubble and the visible wavelength view with Hubble. So how does this work? Well, you know, when you go around to the airport, which we hope to be doing again sometime soon, and you walk through the scanner uses millimeter wavelengths, which is really long infrared, to see if you're wearing something that you shouldn't be when you're going through the airport. So the longer wavelengths are able to go around objects that the short wavelengths cannot go through. Here's an example showing the change of appearance as you go from the visible wavelengths to the infrared. Dramatic change. So the Webb telescope will take these kinds of pictures. They will be beautiful and different. So we'll be looking in the solar system. We can look at all of the objects in the solar system from Mars on outwards. Here are diagrams of two very interesting ones. Europa is a satellite of Jupiter, which you can see with binoculars easily enough. We sent a mission called the Galileo mission to orbit around it and got some nice pictures. And this map on the left shows that the satellite Europa is covered with ice and that there are brown cracks where stuff comes up. More recently, it was discovered that water is spouting out from this little satellite, and we imagine that it might be filled with organic molecules if the ocean that's under that ice is alive. So wouldn't it be cool if you could find out? So we NASA are planning to send a probe to fly through those water spouts, those geysers that are coming up from Europa. Now, the other big planetary mission we're working on now is to go land on Titan, which is a satellite of Saturn, and it is so cold that it's able to hold on to a thick atmosphere. It is a little above the temperature of liquid nitrogen, I think, maybe a little lower, I can't remember. But at any rate, it has oceans, lakes, rivers, rain, thunderstorms, I suppose, that are all made of liquid hydrocarbons. So the ethane and methane are producing these lakes on the surface of Titan. So this is clearly an exciting place to go to look around for things that might possibly show a possibility of life based on something else besides liquid water. So we're going to go there, and we have designed a helicopter that will be able to fly around and take samples and look at the surface of Titan from lots of different places. Very exciting mission. And of course, the Webb telescope will take pictures in advance to make sure that we know what's happening as well as we can. We'll certainly also be looking for exoplanets. Exoplanets are common, as I mentioned before. This is one way that we look at them. When a planet happens to go in front of its host star, blocks a little bit of starlight, and we can say, oh, there was a planet there. We can say how big it was relative to the star, right? How much of the starlight is being blocked. And then we say, well, guess what? Some of the starlight going through the atmosphere of that planet on its way to our telescope might be absorbed by the chemicals in the atmosphere of that planet. So that means we can now do a chemical analysis of a planet around another star. We've already proven the technique with a few planets with the Hubble telescope and the Spitzer Space Telescope. We have now a good long list of planets that we are planning to study, and we know exactly when they're going to go in front of their stars, and we hope to find out a few things about them. What is their chemistry, and especially, do they have water vapor enough to explain or to be consistent with a liquid water ocean? That would help address the question of how far away are the neighbors. Are we alone? Well, I doubt it, but it doesn't mean that the neighbors are anywhere close. This will give us some attempt at learning about that answer. So now to jump back a little bit to that technology, how do we do this? This telescope was first assembled at Goddard Space Flight Center here in Greenbelt, Maryland. And there it is in the upper left corner. The 18 golden hexagons were all attached, proven to work. They all have little motors that move them back and forth. We tested them. We proved they did all that. Then we put them on a shaker. Well, first we put them inside a clean plastic tent, and then we put the whole thing on a shaker to make sure that it would survive the vibration of launch. Then when we were done with that, we put it in a shipping container and put the shipping container in a truck and drove the truck into an airplane, a C-5C aircraft, and we flew it all the way down to Houston, Texas, where we put it inside the giant vacuum tank that they have there, the one that I mentioned earlier with a hurricane. So of course the telescope was safe inside the vacuum tank, but it was awfully wet everywhere else. After we proved that it worked, and it worked fine when it was cold, then we put it back in the airplane, send it to California, and where it is now, and it has been attached to this piece. Includes the spacecraft with all of its rocket jets, electronics, and the giant umbrella, the sunshade. And it's now all together, and it has been unfolded, and we are now folding it up for the very last time to put it in its next shipping container. And this is an ocean-going barge that is capable of taking it all the way through the Panama Canal in Panama. All the way to French Guiana. And why is it in French Guiana? That's because that's French property, and it's where the Europeans have a rocket site. And you could say, well, and why did they put it there? Because it's on the equator, or very close to the equator. It gets you the maximum benefit of the spin of the Earth. So then we will push the button as soon as it's ready, sometime a little after October 31st. We'll go out into space, we will unfold it and make it work. And there it will be in a picture that no human will ever see, because of course we will keep the sunshine off the telescope. So here's what it looked like in our clean room, a big golden beautiful hexagon. And the purplish things that are wrapped up there are part of the structure. We'll show you how that all works in a bit. It is orbiting around, or will be orbiting around, the Sun-Earth Lagrange point 2. So these are places where the gravitational forces of the sun and the Earth are just enough to pull the object around the sun once a year. So it stays in these places. So we're going there. It's a good place to put the telescope, because when you're at L2, the sun, the Earth, and the moon are all in the same direction. It means you can put up a single-sided umbrella and protect yourself from all the heat there. Now, a lot of people have heard about points number 4 and 5 because they're stable. Points 1, 2, and 3 are not stable. So that means we have to once in a while fire our little jets to make sure we stay. Here's our scary movie. This is a couple of weeks of paying very close attention. This is not quite the same story as landing on Mars, where humans have no hope of helping the equipment along. In our case, we have two ways to do everything. So every time we send a command, we say, well, did that work? And if you think about it a while, you decide what to do, but there's always a second way to do everything that you're seeing here in this movie. You look at the picture, you say, isn't that extremely complicated? And the answer is, of course it is. There is no other way, however, to get the science that we're after. And we ask the company, well, is this the most complicated thing you ever have built? And they say no, because of course they also work for other government agencies with 3 letters in their names. So here, as the last stages of unfolding the telescope, first we pull on cables that separate these 5 layers of the sunshade. And then the very last thing is we unfold the telescope itself. There it's putting out this Cassegrain secondary and unfolding the wings that have the rest of the hexagons. So at that point, it's been deployed, but it's not in the right shape and it's not focused yet. It'll take us altogether 6 months to go through a very long and elaborate checkout that makes sure everything is working correctly and that we know how to take the pictures in the best possible way. So that's our thing to do soon after launch. Come on, computer. So now I want to talk just about a few other things that are coming up in our future. Telescopes in space are great, but it's hard to build them and it takes a long time. So of course, our fellow astronomers that stay home on the ground are building big telescopes too. So here are pictures of the 3 next generation telescopes. Giant Magellan telescope, 24 meters across, 30-meter telescope, and the European, the biggest one, the extremely large telescope, 39 meters across, which is 6 times as large as the Webb telescope. So it's a great telescope. It has, however, the problem or challenge that it's at the bottom of the atmosphere. So the same densing atmosphere that limits your image quality and it limits them for this big telescope too. So you say, well, what am I going to do about that? So of course, astronomers invented adaptive optics. If you can measure the light coming in from the telescope, you will see that the wavefronts, which should have been flat because they came straight from the star that you're looking at, and they're not flat because they've been distorted coming through the atmosphere of the Earth. We say, okay, well, let's measure and correct. So until the corrected wavefront is flat and you get a nice sharp picture. So that works if you can figure this out. So it's a solved problem in principle. The ideal way to do it would be to have a bright star near the target that you want to look at. So you focus on the star, then you get a sharp image of everything nearby. So, but unfortunately, there's not always a bright star near where you want to look. So we here at NASA Goddard have been looking into the possibility of having a satellite beacon that we can put near the target that you want to observe and be able to apply this extremely well. So you would be able to get angular resolutions of a few milli-arc seconds. Much, much, much better, like hundreds of times better than what you can get with your own telescope that you can buy from Meade or Orion. So you'd say, well, is that interesting? Well, yes, of course, astronomers are excited about it. But on the right-hand side, I'm showing you that the same technology has now appeared in your eye doctor's office. They have the ability to see the back of your eyeball, correcting for the errors of your own natural lens in your eye to see what's going on in case anything needs some help. And if you're rich enough and really want to have perfect vision, you can use this technique to get 20/10 vision. So I understand that football players have to do this. At any rate, an interesting spin-off. The person who invented this system on the right-hand side is actually the same person who learned how to polish the Webb telescope mirrors to perfection. So if you could do this, well, then here is our story. Let's aim a laser beam down from space at the telescope on the ground. So we're working on that one right now. And now I want to show you the most difficult of all observations, observing planets around other stars. So here's our wild idea. If you could put up a star shade that would cast a shadow of a star onto that telescope on the ground and keep it lined up for long enough, you could do this. So the picture on the right-hand side shows you that if you could work with that giant European telescope and put the star shade in the right place, you could get a picture of the solar system around another star in a minute. So not easy. I'm not telling you that we know how to do it. I just wanted to show you that if we could do it, you could measure. Not only could you measure, you could even measure the spectra of planets out there and show that they have oxygen and water in their atmospheres. So I've been working on that. You haven't seen much in print about it because so far our manuscript was rejected by the Nature Astronomy magazine, but it'll come out one of these days and everyone will see that what we used to think is impossible is actually only just difficult. So I think that's just about the last bit I want to tell you about. I want to conclude with speculation on how far people can go. People can't go as far as we like. We can send robots. We have already sent robots everywhere on Earth. We have sent them to all of the planets. We've sent them so close to the sun they almost melt. And we have sent them digging. We send them drilling tunnels. Robots are great. And eventually we have the smart computers that run them. I'm a little afraid of these things, but it's not impossible for some of our science fiction fantasies to come true when the robots are coupled with intelligent computers. On the other hand, we personally are fragile. We don't like cosmic ray damage. We don't like vacuum. We don't like zero gravity. So if you really want to go somewhere, we need to invent the next generation of space propulsion, which would be some kind of fusion drive. We don't have it here on Earth yet either, but I would say not impossible. So we'll see what happens in the next decades. Not impossible. In the very long term, where does your science fiction imagination go? We're not going to the stars, but robots could if they want to go. So we'll see what the robots are thinking in another 50 or 100 years. So let's stop and have some questions. Okay, questions, people.
Go ahead and unmute yourself if you have any questions.
Just a clarification. This is Joe Comiskey. I enjoyed your talk, by the way, and want to just clarify the launch is scheduled for around Halloween of this year.
Yes, it's
okay, and the working, I mean, the operation of the telescope is about 6 months out from there. Then.
Yes, we're planning 6 months to getting it ready after we launch it.
Okay, thanks.
And sorry, right now I'm looking for my controls on this computer here. So I no longer can see how to unshare my screen. Oh, there we go.
I got it for you.
Thanks. Okay. So more questions.
Well, I had a question. I see mechanically you had function A and function B for doing each thing on the telescope when it's out in space. I was just wondering about the human element. It seems like you got some pretty integral parts like yourself. And I wonder if there's an A and a B of you and the other scientists.
Oh, well, yes. We are a big team. There are just at Goddard Space Flight Center, there are about 15 of us scientists and well over 100 engineers and managers. And at the contractor that's finishing this up, which is Northrop Grumman in California, there are hundreds. So it's a very large team. If I decided that I wouldn't do something, that other people would perfectly well do it. Everyone in a position of authority has a deputy, as you always should.
But you're not kin to the Borg, right?
No, I don't think so. I wouldn't admit it.
What is the thing that scares you the most about this project?
I guess it's the same thing that worries all of the engineers, which is that's an awfully complicated unfolding process. And we've never done anything like it in space. We've done it quite a few times here on the ground. And there's always some little glitch that says, oh, well, we better fix that before we do it again. And so we are now at the point where we have to say, we think it's good enough. But there's always this small chance that we didn't think of something. So that's the big issue for everyone.
Do you ever feel a sense of completeness, 98%? Is there a feeling of that nature?
I think so. We're so close to done now. We've been working on this for over 25 years since I started. And there's only 3 months worth of work left in California. So we're close. Yes.
It's an amazing project.
So what would you say would be the best scenario? What would be the greatest discovery you could make with the Webb in, say, the first couple of years of its mission?
Oh, well, I would love to get a surprise. Where is the surprise going to be? Well, nature has given us surprises in a couple of major areas. One is what happened after the Big Bang. We really did not expect dark matter and dark energy. We still can't see them, but we know they've done something strange out there. So I would not be too surprised if there's some new category of object to be discovered way out there that nobody would ever have been able to guess at with just the equipment that we had before. The other one is planets. There's basically every single thing we know about planets around other stars was a surprise. So why would that stop? I think we're going to get planet surprises.
Wow.
Hi, John. Question: Do you think? Sorry. What is the challenge going to be for maintaining it since it's going to be so far away?
Okay, well, there's nothing we can do to repair it, but there are commands to send. Just like all the other space missions that we have, they have a computer, and the computer has possibility of being reprogrammed whenever there's a problem. And we have 2 of everything. We have 2 sets of cameras in the near infrared camera. We got 2 electrical windings on every motor. We got 2 of everything where we possibly can. So that's how we deal with random part failures. Yeah. And by the way, although we don't have any way to get there, we are making preparations that if we ever do, we would be able to latch on to this telescope and make a repair robotically.
I've watched a couple of videos of the unfolding process. It's very, very impressive, and looking forward to watching it actually happen.
Yeah, me too.
You mentioned this is a cryo, well, it's a cold mirror. Is there anything to cool it other than, or is it just the being in space shielded from the sun that's sufficient to cool it?
The telescope is all cooled passively that way, just radiating its heat away to space.
Okay.
But we do have one instrument inside that needs to be at 7 degrees Kelvin. And so it's got its own refrigerator. We've got a compressor that compresses helium gas and sends it down through a long tube. And when it gets down to the instrument, it expands and cools things. But we will not run out of it. It's supposed to last forever.
I think you said you've built things for 5 years, but you expect it to last 10. Well, you've designed it so you think it'll last 10. Do you expect there will be any surprises as with the Hubble and it'll last even longer?
I hope so. Yeah. We have different stuff from what they built Hubble with. Hubble was built with technologies that's getting on towards 40 years ago now that they started designing all that. So we have new stuff. We hope that it's more reliable. As an example of something that we think is more reliable, the Hubble uses little gyros, little tiny spinning balls about 1 inch across. to help keep it pointed in the right direction. And we've replaced those with something that has no moving parts. It's called a hemispherical resonator gyro. And it works by acoustic waves propagating around in a crystal. So it should not wear out. So we do what we can to make it better.
Cool.
To create these objects that we send out like this, how many new discoveries of tools and, like you were just talking about the gyro, how much of that happens?
Well, we started off and made a list. We said we need 10 inventions before we can do this project.
Whoa.
So how are you going to get 10 inventions? Well, first you say, everybody world, we need 10 inventions. Who can make this invention for us? Send us a plan, send us a proposal. And if we like your proposal, we might send you some money. And so that's what we did for all of them.
That's amazing.
So it's mostly commercial inventions where we called for them, paid for them, and got them.
Can you talk about what some of the others are?
Yeah, well, okay. So number one was the mirrors. How are you going to get those big mirrors? Number two is after you got them, how do you focus them? There's got to be some math and some algorithm that says measure this and do that, and you'll be able to adjust them. Then there's how do you unfold that big thing? There's hinges and frameworks. Then there are two different, or actually three different flavors of detector, infrared detectors that take the incoming photons and turn them into electrons that you can count. And so we knew what the possibilities were, but we said we need better ones. So we did that. We called for those inventions. Then that actually had some trouble because we got a whole batch of good detectors and then they started going bad on the shelf. Okay, got to figure that out. So we got a new batch that was fixed. We had to figure out that little refrigerator that I mentioned, that I said we needs to have helium that will cool the one instrument down to 7 Kelvin. Okay, ran a competition for that one. Need to have a little amplifier to put down in the next to the detectors that will convert the detector signal into digits and send it all the way up to the warm set of electronics. So that's an example. That's not quite all of them, but most of them.
I think the most astonishing thing to me was when you had the slide that described the actual mirror as being 2 millimeter thick beryllium, and yet somehow you're able to make it reasonably rigid so that it actually comes to a focal point. I think that's absolutely astonishing.
Yes, I think so too. I'm just amazed. But we said we had to have it, and we ran a competition, and that was the best answer.
I had a couple.
Mhm.
This goes back to Kobe. I have fond memories, and I have it on VHS tape, and I meant to watch it, but I couldn't find it. But I recorded Nightline with Ted Koppel back in 1989 when the Kobe data first came out. Were you on that? Were you part of that show?
I don't remember Ted Koppel.
Okay.
So maybe not, but the launch was November 18th of 1989.
Right.
And our first scientific report was in January 6th or 10th or something of 1990. So.
Okay. I'll dig that out one of these days. I tried to find that on YouTube, but couldn't find it. So I figured I'll digitize it and throw it up there, and it should be pretty fun.
Yeah.
Another question is, I was reading recently how, of course they say the universe is infinite in extent and all that, but that might be affected by gravitational lensing of the CMB. Can you elaborate on that?
Yeah, sure. Gravity bends light, like it affects the motion of particles. So it bends it a lot. You might not expect, but you calculate how much gravity is there for all the galaxies between here and the Big Bang. And a particular ray of light will be deviated by 1 or 2 arc minutes, which is bigger than the resolution of your eye. So it means that although that pattern of little random dots on the sky from the Big Bang is random, it's not, it's got a pattern to the randomness because it's been, all those spots have been shoved around by the gravitational lenses of the galaxies. So you'd say, how can I ever find that out? But the mathematicians figured it out, and you can tell that it's happening even if you don't know exactly.
Okay.
Somebody likes math.
Yeah, some of us do, and some of us live on it.
Any other questions?
The detector that requires a 7 degree Kelvin, is that because of the wavelengths of light that are going to be looked at?
Yes, it's silicon doped with arsenic atoms, and it has to be cold. Otherwise, the heat in the detector itself will cause spontaneous electric currents to flow, even if there's no light coming in. So that's what that's for.
Thank you.
Got a real quick question. This would probably relate to the Hubble telescope, anything like that. How is it aimed? I mean, are there as a little jets or
Oh yeah,
how does
actually,
that work?
we do it mostly the same as they do with the Hubble. The Hubble and the Webb both have big spinning wheels. So when you want to turn one direction, you push on the wheels and it goes the other way, because the total is a fixed quantity. Push on the wheel, it goes one way, we go the other way.
Okay.
So the Hubble does it that way. The Webb telescope is much bigger, and so it doesn't go as quickly, but it does it. We also do once in a while need jets because, and this might surprise you, the sunshine. The sunshine is pushing on that big sunshade, and it's like a solar sail.
Mhm.
So the force is small. It's like the weight of a fly here on Earth, but it's enough that if you didn't do something about it, the telescope would turn over. So eventually that means you might have to fire some jets.
That's amazing.
Yep.
So does that mean that you're gonna have to keep fuel and other things aboard this?
Yes, we do. We carry
And will the weight-
200 kilos of fuel to move this 6,000 kilo object around.
Oh,
Hmm.
Doesn't take much, but it does require some.
So when the Webb telescope is collimated and focused, is its first project going to be like a deep field?
Actually, probably not. That's hard. So we need to make sure that we know how to work it, that we're not going to waste our time with the wrong exposure settings or something. So we will practice, of course, but then we probably will say, prove it to me that it's really working for that before we spend a week or two of precious time on that particular project.
That makes sense.
Yeah. So we do have already a choice of what we're going to do for the first year. And so we're busy planning the schedule of exactly when do you do it in what order, so that you get it most efficient.
right.
What's the round trip time for communicating with the James Webb?
10 seconds, 5
Oh, that's
seconds
not
each
bad.
way. Yeah, it's not like Mars.
Is there a safe mode for this thing if something happens?
Oh yes, all these missions have safe modes. If you don't know what that means, it means if something goes wrong, you can retreat to a place where you're pretty sure the telescope will be okay. That means it's not going to tumble, it's not going to spin, it's always going to have the correct surface facing towards the sun.
Any other questions? Well, hearing none. Thank you very much, Dr. Mather, for joining us. It was an absolute pleasure to have you as our guest speaker.
Well, thank you, Richard. It was a pleasure to talk with you. You have great questions.
Thank you
Wish us
very
luck.
much.
Wish us
Thank
luck.
you, thank you. Thank you.
So excited.
Thank you.
Okay.
We are looking forward to the launch.
Yes.
Thank you.
Thank you
Okay,
very much.
we'll talk with you then.
Yep, bye-bye.
Bye.
That's not what I want. Hi, Dave.
Hey, how you doing?
There we go. Remove spotlight. Well, okay. It's okay for me now. All right, let's jump right into the president's report. The very first thing that I have is Aaron strikes again. So Aaron Roman has completed the Astronomical League Urban Observing Program. He is certificate number 224. So Aaron, do you have that certificate to and pen to hold up and share? I'll spotlight you so we can see it.
No, I don't have them in front of me. If you want to wait 30 seconds, I can go get them.
Oh, we'll come back to that later then.
All right, I'll be right back.
Go, go, go.
Well, shoot. How do you? Okay, so we'll come back to that. And I wanted to mention several things as we get into observing season now. So let me share the first thing here. Is I tried to put, little ads in the newsletter to remind people that we have this program. So of course we have some equipment that you can borrow. I'm eventually going to change the name of this page from telescopes to loan to equipment for loan, because we have a lot more than telescopes now. And so the telescopes for loan page shown here is located under the resources tab. So you just go to telescopes for loan. Eventually I'll probably change it to equipment for loan. And then you can scroll down here and you can see that Arya is the manager of the program. So if you want to check out most of this stuff, you can contact him. There is one exception now that I'll mention. But let me show you real quick the things that we have. I'll first mention the thing we don't have anymore. We used to have a short tube 80, but unfortunately someone walked into Arya's garage and stole it.
Oh,
So that's gone now. And but we kind of replaced that with something a little bit better. We have this nice pair of Orion 25 by 100 binoculars on a parallelogram mount that was all donated by Becky and Kalmansia. So we really appreciate that. And again, you can check this out for at least a month and use it. So it is a great instrument to scan the night sky. So you can see we have a list of what comes with it. And we have the checkout form that you can download. It's just a standard PDF file. And if you're afraid of the dark, and like a standard solar astronomer, but want to still observe, you can check out our Coronado Personal Solar Telescope, our PST, that comes with the TeleVue telepod shown here. So you can observe the sun in H alpha. You can check out prominences and filaments and stuff like that, which are really fun because they're dynamic. And then if you're looking for a serious telescope, we have the Celestron 8-inch Schmidt Cassegrain telescope. Back when I sold telescopes, I sold a ton of these because they're really quick and easy to set up and easy to use. So you can do some serious observing with this scope. It's an 8-inch Schmidt Cassegrain. And then most recently, we have a camera that you can use. So if you already have the setup to do imaging, you have a telescope capable of doing time exposures, you can check out our ZWO ASI 294 Pro camera. This is a cooled CMOS camera, so you can do some pretty serious imaging. And this is one of the most popular imaging cameras today. And you can see it comes with all the standard accessories, including an AC adapter to cool it, because it doesn't come with that standard. And again, we have the checkout form there. And I also want to talk about Owl Observatory again. Is we do have observing tomorrow, and I might get out there maybe an hour early or maybe 2 hours early, because when we were out there last and I first walked into place, I was like, who spilled these raisins all over the floor? But they weren't raisins, they were dead bugs. So we need to clean those up. And there's the general array of cobwebs that would be nice to clean up. And if we don't do it tomorrow, I definitely want to do it before the public observing sessions begin. So if anyone wants to join me and clean up the observatory a bit, a little bit of vacuuming, maybe a little bit of dusting, you can just email me and I'll let you know if I actually do decide to go out there a bit early. I wanted to mention the Owl Observatory User's Manual. That is still a work in progress. I work on it, just a little bit by little bit. I'm kind of at the point where I really need to go out to the observatory to work on it as questions get raised in my head. And so I've been kind of slow on that. Part of the reason is I know largely a lot of people aren't going to use it or look at it or use the observatory. So there's not too much motivation yet. But if people really start getting anxious to use the observatory, that'll increase my enthusiasm for finishing that project. For those of you that took the training program, I mentioned there's no user form, or no online form to fill out, but that has changed now. So let me show you that. So under the Owl Observatory menu on the website, there's a new addition here called the reservation form, and it does require a password. So if you do take the training session, I will give you the user manual, but since we don't quite have that yet, I will just email you the username and password. And so we have the calendar here. Obviously, it's pretty empty because no one really knows the password yet but me. And you can see I put some of the member only stuff on there. The public observing session, we're doing some stuff with KNC campers during full moon, so no one's going to really miss the observatory then. And then we have this form you can fill out. So of course, remember, you can use the observatory day or night. Of course, we have all the proper accoutrement to use the telescope at night for visual use, and most of the accessories I want for nighttime imaging, but not everything yet, but enough to actually do some imaging. But of course, we have stuff to use the telescope during the day too. We have a 90mm Coronado hydrogen alpha filter. So if the PST is just too small for you, you can thread on the Coronado 90 filter onto the TeleVue out there and do some serious H alpha observing or imaging with the camera that we have out there. And I mentioned the training sessions. I did several last summer while we were shut down. But if you, if you're new to the club or not new, but still want to learn how to use the observatory or relearn how to use it, again, email me and I'll see if I have enough people to schedule a training session. Maybe we can do an unscheduled one this month, or we can throw it on the Prime Focus schedule for next month. So again, if you want to learn how to use Owl Observatory, contact me. We have a very nice setup out there. We have of course, we have the observatory with the new Leonard James Ashby telescope inside. We have the TeleVue on there now, so I can show you that. So if you've never seen it, this is our new telescope in the observatory. Of course, the main instrument has been in there since September 2019, but then the stupid pandemic happened, and not that many members of or none really of the public have looked through it yet.
Right.
One thing I also wanted to mention, Kevin did not join us again. So he's been kind of complaining about Facebook. He said if it wasn't for the KS page, he would get rid of Facebook. He has been updating it a bit recently. But he hasn't been doing Instagram at all because he's kind of sworn off social media for a while. So if anyone is interested in perhaps working with Kevin or possibly taking over the Facebook or Instagram page or both, contact me. I can easily hand over the Instagram page to you today because I started it. I know the password, I can pass that on, but I absolutely do not do anything with Facebook because it is pure evil. So I can't do the Facebook page at all. So if you're interested in helping out with the Facebook page or Instagram, again, you can contact me. Membership update. We currently have 236 memberships. We did pick up one new member today, which could be 237, but I'll probably contact them because I was going to mention the next thing here is if you are thinking of joining the Kalamazoo Astronomical Society right now, don't do it. Wait, because according to our bylaws, I think it's the bylaws, it could be the Constitution, doesn't make any difference, but according to that, if you join around or join on July 1st or later, your membership is prorated. So if you join on July 1st on a one-year membership, you get the rest of this year for free and it won't expire until 2022. A two-year membership on July 1st and it won't expire until 2023. So I did already refund one membership to one person because she even paid to use the remote telescope. So even then, that's prorated too. So if you haven't used the remote telescope yet, you can join or pay for that on July 1st. Of course, you can't use it right away because it'll be shut down by then. But you'll be that subscription will be good till the end of next year. So it's a really, really great deal to wait. And as mentioned in the newsletter, she's probably here somewhere, is Kelly Cloisterman has volunteered to record, edit, and post the meetings on YouTube once we start meeting in person again. But, I'm sure she's a very busy person. She can't attend every meeting. So it's always good to have a backup or two. So I promised I would keep mentioning that. And so again, we're looking for perhaps a team to make sure we keep at least doing live meetings or streaming meetings online, or at least recording them and posting them on YouTube shortly thereafter.
She is here tonight, Richard.
Okay. So I don't know if Kelly had anything to add, but we can chat about that later. I wanted to mention the winter solstice dinner again. As you may have read in Prime Focus, we're looking for a restaurant to go to. That is my preferred thing. We talked about the possibility of doing one of these banquet halls where we can cater food, but that's just one more thing to handle. So, restaurant has everything that we want under one roof. I did get a couple of good recommendations so far that I need to look into, but I'm always willing to listen to more. So if you know of a good restaurant that can hold between, 70 plus people for the new dinner that we'll do in December, please let me know. And the very last thing I wanted to mention, just because I'm sure many of you also have fond memories of this, but tomorrow is the 9th anniversary of our last Transit of Venus event at Warren Dunes State Park. So we had probably at least 700 people show up to this on June 5th, 2012. So you can check out the gallery page here. This gallery is in the special event section. So you can go to the gallery menu, click on special events, click on the Transit of Venus, and that'll take you to this gallery page. And so, of course, we had absolutely perfect weather. It was cloudy further inland, but we enjoyed clear skies. And I really miss what I called telescope row. We basically had this, line of, well over a dozen telescopes set up right along the edge of the concrete pad they had there, for barbecues and hot parties and stuff like that. And of course, many of us took, pretty cool Venus transit images. So I just wanted to mention that in case you are a little nostalgic for stuff like that, like I am. So that's all I have for the president's report, but let's double back and let's see. Aaron, you want to show us your certificate and pen? You got to unmute yourself, but you can just hold it up. We don't have to hear you.
Oh, okay. Right. So here's the certificate, and I'll smile nicely so you can take a picture.
There we go. Perfect.
All right, good.
Yay, Aaron.
This is the pin. Get that in focus.
Oh.
It comes with a little note. He says, a note on the urban program pin. Our designer tried for a little optical illusion. Viewed right side up, it represents the desert scape, but viewed upside down, it's a cityscape. This represents the best and worst of observing conditions in juxtaposition. So you can kind of see it. But it's a nice idea. The one thing I found that I enjoyed the most about the urban program wasn't that I was sitting in I like my backyard. The pandemic and my backyard have been nice. So that's why I picked up and doing this program. But everything on the list has a really nice high surface brightness. And that makes it easy to observe. So if you want to grab up this list just to share with, anytime you're out observing with any of your friends or family, and you're like, what can I show them that they'll actually be like, oh, that's nice. This is the list, because it's all a bunch of bright objects. And it comes from a bunch of different catalogs. So it's got the Messier, it's got the NGC, it's got the Malott and the Trumpler and Stock. It's a bunch of different catalogs that they draw from to build the list. So I don't know, even if you don't do it for the urban program, if you scoop up this list just to look, it's all the good objects you're looking for.
All right, great. Did you and/or Don want to talk about the possibility of a new SIG for AL programs?
Sure.
Let's do that now.
So I have emailed pretty much everybody who has completed one of the Astronomical League's observing programs and asked them, hey, are you still working on anything, you know, and would you be interested in getting together as a group to do that? We'll do a full emailing list maybe after this meeting and kind of mention it to see if we have any interest. But the Astronomical League obviously has observing programs and people are at various stages during those, and sometimes they're difficult to navigate, and especially getting started, it's not the easiest website to dive into and be like, oh, this is my observing program. So especially if anybody's saying, hey, I don't know where to get started, I'd be happy to put my email in the chat here so that you can say, help me find the first program so I can maybe dip my toes in this and see if this is something I want to do. Don, did you want to say anything?
Well, I just want to say the perfect opportunity to start these lists would be at our public, what should we again have public observing sessions, which I'm hopeful it's going to start pretty soon. This would be the perfect time to come and talk to Aaron or me, particularly Aaron. He is the secretary and he does have the best knowledge currently of the observing programs available, but either he or I can help you choose a viewing program and get you started on it. We can, right there at the public viewing, at least get your first, handful of objects under your belt.
That reminds me, Aaron, I owe you an email. I saw it, but I've been out of town, just a whirlwind of activity with my parents. So, so forgive me for not answering your email.
Well, the one thing about saying, oh, I'm going to go start a SIG, I'm going to be part of a SIG, everybody's like, another commitment. I'm hoping that it isn't more than that. I hope it just gives us a good excuse to maybe do more observations and be able to share with your family and friends, more effectively as well, so that it's more enjoyable for everybody.
And outside of the two areas that we would probably go to, or two locations, I should say, viewing locations would be, of course, the Kalamazoo Nature Center, and the second place would be the Richland Township Park. And those are the two places, at least that I'm familiar with, that would get any viewing program started and finished, particularly at the Richland Township Park location.
Right. And if we get a couple of email responses saying, hey, I think we can maybe do this. If I get 6 or 8 people in a group, maybe we'll set up a Zoom meeting to start, or now that we can get together, depending on the comfort level of the group. We can get together for maybe about an hour and discuss it and maybe take some recommendations. So if you got ideas out there, definitely please put them out.
Yeah, so think this is me saying to Aaron, think of Aaron as a chair of this group, and I'll be his right-hand man.
He'll be the deputy.
Right, I'll be deputy.
Okay, speaking of SIGs, let me give you an update on the new astrophotography SIG. We did hold our first meeting on, gosh, what was it, May 19th or something like that? I forgot already. But we had a pretty good turnout, more than I thought. It was about 35, 37 people actually showed up on Zoom, which I thought was pretty impressive. And of course, the first part of the meeting was intros. Many people shared images. I mentioned that Josh Taylor Lyman stole the show with his mosaic of the Orion region. That was just a really impressive image and a great deal of work. It's like 1,200 images he had to stitch together. So that was very impressive. And then we got down to business and talked about the future of the SIG. And I'll just give you a quick summary. If you haven't read the newsletter yet, I'm sure most of you haven't, is we're going to meet in person between September and May. So we'll try to do a hybrid meeting too. We'll try to have in-person meetings at a location to be announced, because we aren't really sure where to meet in person yet. But we'll try to do them simultaneously on Zoom. But if that's impractical, we'll just record them and post them on YouTube afterward. so people don't miss out, but we want to make it interactive. And we'll start at 8 o'clock because some people said 7 o'clock is a little too early. So we'll again meet at 8 o'clock between September and May. And there is the possibility of informal meetings in the summer, but I envision the summer will be spent mostly trying to do workshops or imaging together. So to that end, I've scheduled a astrophotography workshop for Friday, June 18th at 9:30. You do have to register for that. I don't know if anyone paid that close attention to the little article in the newsletter about it, but if you want to come out and take pictures of the moon with your camera, or if you don't have a camera, we will also use the ZWO ASI 071 camera that we have in the observatory to do some lunar imaging, you know, take some videos and you can stack them later and hopefully create a beautiful image. So just a reminder, if you do want to participate in the workshop, you have to register for that. You can just email me directly, but I say in the newsletter to use the contact form because I don't want to put email addresses in the newsletter because they might get lifted by bots and you'll get spam like crazy. So I try to avoid doing that these days. Pete, did you have anything else to mention about the first SIG meeting?
No, I think it went really well. Really looking forward to hearing from everyone who joined. The experience ranges are wonderful. A lot of good, it's going to be a really great time. I think there's a great group of people and looking forward to hopefully everyone coming on board. I think it's going to be a good time.
Richard,
Jack, are you airing out your cast or do you have a question?
I'll both. You suggest the newsletter, a portable hard drive. How big should that be?
The movies should be at least a gig because they're, unless I chop down the resolution a bit, but they can get pretty big. So I'd have at least a nice terabyte drive with you.
Okay.
If worst comes to worst, I can throw them up on the cloud and you can download them. But
hard drives are readily available locally, or we gotta buy them online, or what?
No, you can get portable hard drives at Office Depot or Office Max, whatever the hell they call it now. Even Best Buy will have them.
Okay.
But they're getting pretty cheap. There's probably even little flash drives that have enough storage for videos, just as long as you don't have too much else on there.
Jack, Costco sells them too.
Okay.
There you go. All right, moving on, observing and imaging reports. We did have our first member-only observing session on May 22nd. I think Aaron or Don told me we had like 21, 22 members show up, so that's pretty good for a member session because, as I often mention, this is not an observing club. So to have that many for a member-only event is pretty impressive. Again, the night was pretty much dominated by the moon, so that kind of washed everything else out, and there are no planets to look at, but we did try to do some double stars and some of the brighter deep sky objects. The first problem we had, or at least that I had, and I'll show you, is when I first got out there, I felt guilty for having to move this because I peeked inside and there are 4 robin eggs in a nest on the rail just below the roof, so they wouldn't get rained on. So I had to kind of slide the nest down on the rail, which the robins were not very happy about. And then I picked them up and put them back where they were under the roof on the rail, and hopefully they're okay. But I guess we'll find out tomorrow, see if they hatched, and I'll be a little more leery to move the roof with baby birds in there, but maybe we'll have to have someone spot it and make sure they don't fall over. But the nest is on there pretty well. So that's what we had to deal with there. And for the first time, many of us saw a line of Starlink satellites. I counted about 40 of them. It was horrifying. So did anybody else want to add anything about the member-only session or any other observing sessions you've done?
I just want to say that, of course, I forgot to think about our members-only session. Yeah, we can start members-only observing club people.
Last month, you saw Venus and Mercury, and pretty close proximity to each other, and I got my family and I all out, not on the same location. Some of them were on different parts of the state to look through binoculars at the crescent moon, which until you knew where it was with binoculars, you could not see with a naked eye. So everybody was very impressed with that. If you haven't seen it yet,
Is that the one that's like 29 hours old or something like that? I think it was. Yeah, I saw that too. And I would not have seen, I could hardly see it with binoculars,
right.
At least at first.
Absolutely, yeah. No, it's a neat experience, and I think everybody kind of liked it.
Yeah.
So.
Any other observing or imaging reports? Pete, no new images to share?
Nope, unfortunately, work and life has gotten in the way of my imaging.
Oh, that's good. It slows you down.
Yeah,
Doesn't make the rest of us look bad.
No, there's a lot better imagers than me here. I can tell you that.
Yeah.
After that SIG, man, that big, huge mosaic, man, that is.
Yeah, that was pretty good.
That was pretty good.
All right, so if there are no more observing or imaging reports, we'll move on. Astronomical news and events. Sounds like NASA's going to send 2 more probes to Venus. My first reaction was, what about Uranus and Neptune? Those are screaming for orbiters, but I guess we're going back to Venus instead.
They launched a cargo ship yesterday, and because it was daytime, I was able to watch the booster land back on the ship, and they had the camera looking down, and just closer and closer. Oh, there's a ship in the water, and all of a sudden it's touching down on the ship, and that was really impressive to be able to watch the whole thing live in the daylight like that. It was really pretty cool.
Okay, and of course the big news is Orion telescopes and binoculars is purchasing, I guess, what's left of Meade. If you haven't kept up, which I wouldn't be shocked if you hadn't, a couple of years ago, Orion's parent company sued Meade's parent company because they were kind of doing this price fixing thing, and Meade had to pay up like couple tens of millions of dollars, and we kind of knew Meade was going to be in trouble after that, and so looks like Orion is taking advantage of the damage that they did and is going to buy up Meade. Hopefully nothing will change. Both companies make nice telescopes. Meade's kind of gone toward the higher end with some of their more stuff for regular amateurs. For me, Meade started taking a turn for the worse when they went public some time ago. That's probably been about a decade, because they started selling, the crap telescopes in department stores, and to me that kind of ruined their rep a little bit. So hopefully stuff like that will come to an end. They won't sell the junk telescopes in department stores anymore. Even Celestron does that to a degree. I remember we had World of Science, Crossroads Mall, and they sold the crappy Celestron telescopes with the little 0.965 inch eyepieces. So if you do see a lot more Meade telescopes on Orion's website here in the future, that's why.
Yeah, reading the news release, it sounded like Orion's committed to letting Meade continue on with their high-end stuff and be like their own brand and division. So it looks like that's encouraging. So, even put some development money and actually improve their customer service. So
yeah,
fingers crossed. It was good to read.
That's the take I got out of reading the press release. They're creating Meade Instruments as the new corporation. And will manage that stuff. And I understand, Pete, what you were saying. That's what I took also, was that to continue on as a separate entity.
Yeah.
I will say, as a former telescope dealer, I don't know what your experience was, Pete, but Orion did have the best customer service, or at least the best dealer service, when you called up and needed stuff. Meade was the worst, because I remember Dave Wolf, cast member Dave Wolf, brought in a Meade CCD camera that needed servicing, and I called Meade over and over again and could never get anything hooked up. And then people would come in the store and say, I want to buy this Meade camera. I'm like, I'm not selling it to you because if you have trouble, I can't get it serviced. So Orion was the best. I enjoyed working with Dave Thomas, not the Wendy's Dave Thomas, but the Orion dealer. Dave Thomas. I have no idea if he's still there.
Yeah, no, I enjoyed working with Orion back into the day. That was a good company.
I loved calling Teleview too, because they would get kind of sassy in that New York kind of way. That was fun. Any other astronomical news and events? Nothing? All right, moving on. KAS Event Horizon. Tomorrow, we have our last member-only observing session. So the weather looks fantastic. So please join us at roughly 9:30 p.m. I might have the gates open a little bit earlier if you want to set up your scope earlier. So if you want to try to come out earlier, that should be fine. You can always email me to double check so you're not waiting at the gate too long. But again, this time the moon will be out of the way. No stupid moon to look at. So we'll be able to look at galaxies and Ursa Major and all kinds of other cool stuff. So join us tomorrow at 9:30 at the Nature Center, especially if you haven't seen the new telescope yet. We have our next board meeting on Sunday, June 13th. I will send out a reminder to the board later this week. So you can tell me if you can't make it, or tell me any items you would like to appear on the agenda. And if any regular members would like to attend the board meeting, just email me and I will send you the Zoom info. We don't make you register for that one. I just send you the meeting ID and passcode. And as mentioned, we'll have an astrophotography workshop if skies are clear on Friday, June 18th at 9:30. Our target will be the moon. And so we'll use hopefully your DSLR camera to take pictures of the moon. There's a list of required stuff to bring if you do bring your own camera. And even if you, again, don't have your own camera, we will use the camera in there to do some short movies of the moon. And we're going to launch our season of public observing sessions at last on Saturday, June 19th. We've had a bit of publicity already. There was an article on MLive or the Kalamazoo Gazette, and I got to let somebody in. And I just did WXMI, Fox 17 this morning. So if you go to their morning news section of their website, you can see that. I tweeted about that too. So hopefully we'll have big crowds for our public observing sessions because, we have that new telescope angle to go with. Hopefully a lot of people will come out and see the new telescope. I'm just so super anxious to share that thing. Prime Focus, the usual deadline for articles is June 15th. So if you have, observing reports, you want to write about a memorable night of observing, you want to review equipment or anything else, you take like a summer trip, like an astronomically themed trip to an observatory somewhere, write a report about it and put it in the newsletter. That's what the KAS is all about. As I always mention, I want to put or keep the society in Kalamazoo Astronomical Society. Part of that is sharing your experiences with your fellow members. Who's making all that noise in the background?
Not my dog. It's not my dogs.
It's not your dogs. Any other items anybody wanted to mention? Not on the agenda? Or anything anybody wanted to share? Josh, we've been talking bad things about you. I'm guessing that's why you logged on, because we're very jealous of your Orion mosaic. Did you have that handy, by the way? Do you want to share that real quick for people that haven't seen it yet?
I do not have that handy. I'm sorry.
Okay.
I'm on my phone and it's downstairs on the computer. I just got done with dinner and a family.
We'll keep people waiting until Astrophoto night then. So you better be there, or we'll hunt you down like a dog.
Yeah.
Okay. Next, the next general meeting will be delayed 1 week, as it always is, because of 4th of July. So we'll meet on July 9th in the real world. This will be our first in-person meeting since March of 2020. So we'll be meeting at the Kalamazoo Nature Center, specifically in the amphitheater. If you don't know where the amphitheater is, but you know where the observatory is, just pretend like you're walking to the observatory and keep looking right, and you can't miss it because it's right next to the observatory. It's just south of the observatory. So I'll try to mention this in the newsletter and reminder emails. You might want to bring bug spray. Sometimes we have mosquito issues in the amphitheater. Sometimes we don't. It just depends on the way the weather is. So bring bug spray. Since we'll be in the open, everyone should be able to go maskless, maybe except you unvaccinated people. You know, if you're not vaccinated, what the hell are you waiting for? Do it already. If there's nothing else, we will go ahead and officially adjourn. And again, I hope we see you all tomorrow.